Today I'm going to present the results of some testing I did with a GNU Radio receiver along with a typical NASA vendor modem modulator. So for this conference, the conference leadership did encourage papers based maybe more on demonstrations than simulations. They also encourage presentations from a kind of tutorial perspective. So I'm going to try to do that. Hopefully this will be useful to new users. I'm only probably a user for about a year myself. So that's what I'm going to try to do. My background, currently I work at the NASA Goddard Space Flight Center for a contractor named Peraton. The one disclaimer is really all the materials in here, the presentation, the associated paper that will be in the proceedings is really based on my own personal perspectives, personal opinions, not NASA's. So about 1 year ago, I was looking for alternatives to MATLAB Simulink for some communication system simulation activities. So I went ahead and I found that GNU Radio could be a good fit for that, a good cost-effective fit, low cost. And so I also found out that GNU Radio could really be used as a software-defined modem, a low-cost one, at data rates NASA typically uses at S-band. So I went ahead and started developing the GNU Radio SDR receiver and then tested it along with a typical NASA vendor modem modulator. So again, I'm trying to do this from a tutorial perspective. To describe how I developed the GNU Radio SDR receiver and then tested it with the NASA vendor modem. So again, the scope will be kind of a tutorial perspective. Hopefully this will help new users so that they can maybe quickly build or implement a good cost-effective GNU Radio SDR receiver or modem. Okay. This chart is high level for the test configuration. It's a back-to-back test configuration. The NASA vendor modem modulator is on the left. It transmitted over a coaxial cable, 50 ohms SMA with a 1.2 gigahertz intermediate frequency to the GNU Radio SDR receiver. Used BPSK and QPSK. Okay, this chart shows the parts I used to develop the GNU Radio receiver. The Dell laptop, which is this one actually here, Linux, and the GNU Radio software version 3.7.11. The RTL-SDR hardware dongle, just $28, commercial off the shelf. Has a USB interface on one side to connect to the laptop, has an SMA 50 ohm interface to connect to the IF signal. And the dongle does the frequency tuning, and it also down converts to digital IF, which I sometimes call 0 hertz IF. And I just got that on Amazon. The BPSK test case, this would be the flow graph, the GNU Radio flow graph for BPSK. And on the left is the RTL-SDR source block that controls the dongle. The other main blocks are the polyphase clock sync block that does the symbol synchronization, the Costas loop that does the carrier synchronization. And the other blocks are really support blocks, so I'll be showing it on the next chart. Okay, the support blocks for real-time monitoring during the tests had the time sync block, which does the oscilloscope functions, frequency sync block, have an IQ constellation sync block to monitor carrier synchronization and performance. For QPSK, the flow graph was pretty similar. The only difference was the Costas loop there. The order is now 4 rather than 2. And all those blocks at the bottom, like the multipliers, I used those to resolve carrier lock phase ambiguity. So since this is really a tutorial type presentation, I wanted to, since I was a new user, list a couple things here that gave me trouble when I was developing the receiver, the TAPS parameter in the polyphase clock sync block, and just getting that RTL-SDR source block into the GNU block library. So on the clock sync, basically you need to type in a lot of stuff there for the FIR, root raised cosine filter, and then it is a function of a few parameters there, the samples per symbol, the root raised cosine roll-off factor. L would be the length of the prototype filter for the block. That probably could be an entire presentation on itself on that and how the block is built. So you just, for a new user, just put in 11, maybe 13 will work, and you'll be off and running. Number of filters in the polyphase filter bank, set that to 32 is a good number that I used. So all you need to do is type in the FIR, root raised cosine, 32, 64, 10.5, and 704, and that should get you off and running pretty quickly, especially if you're a new user. The C++ code is in GitHub. It's on the GNU Radio GitHub, and that really does provide a lot of useful insight into the details of the blocks. I'm still going through it myself. For the addition of the source block, the RTL source block, I found this one command for the Linux terminal, sudo gr-osmo SDR, and that allowed me to load the entire GNU Radio software along with the source block then in the library. The development process, I did that in 4 steps. First, the simulation. I basically just used the GNU Radio simulation modulator blocks along with the receiver blocks to get going, get the hang of GNU Radio. Then I went out and bought the RTL dongle. It came with an antenna when I bought it. So I tested it with FM stations, get the hang of the dongle, get the hang of GNU Radio. Then I went out and bought a signal generator, a low-cost one for BPSK, and all it could do is a 1010 pattern. I brought that with me, so hopefully I can get all that running here. There's some time. And then the last step was to go to the remote facility where the vendor modem was to do the actual testing. So the test approach, again, I did 2 test cases, BPSK and QPSK. The settings on the blocks in the flow graph were pretty much the same for both modulations, except for the Costas loop block. The order was different, and that was about it. And then I used a repeating 15-bit pattern for the testing. So during the testing, the performance was good. I was able to recover the transmitted bit stream from the modulator, achieve symbol synchronization lock, achieved carrier synchronization lock. The next charts will show how I concluded that. Basically, this is a snapshot of the time sync block display during the testing, and this shows the 15 bits. And I had it refreshing at the same rate, so I could look at it for 5 minutes, 10 minutes, and make sure things looked good and weren't slipping. The frequency spectrum during the test, from the frequency sync block display, a snapshot here. You can see the oscillations maybe about every 60 kilohertz are due to the repeating bit pattern. If I had a much, much longer bit pattern, it would look more like the BPSK from your textbook. So the IQ constellation before the Costas loop block. This is before I removed the residual frequency offset between the vendor modem modulator and the RTL-SDR hardware dongle. So even though they're both set at the same frequency, 1.2 gigahertz, there's a little difference, so that rotation is there. This is just a static snapshot, so maybe when I do the demo, you can see the rotation that occurs. Now, after the Costas loop, now you have the more typical good IQ constellation that you expect with BPSK. So this is after the Costas loop, and now the residual frequency offset has been removed. So this chart really just shows the residual frequency offset removal before the Costas loop and after. Equation 1 would be the incoming signal before the Costas loop out of the dongle, and equation 2 at the bottom, that would be for after the Costas loop, and it's been removed, and yet now you just have the phase that you want. The 2 phases for BPSK and the 4 phases for QPSK. So the conclusions on here, within the scope of this initial testing, now it's just a subset I tested of typical NASA waveforms. Didn't test all of them, for example, phase modulation with a subcarrier. But within the scope, the GNU radio receiver was compatible with some NASA modems, waveforms, and also data rates that they use at S-band, up to a couple megabits per second. So what can we use GNU radio now for, maybe, in my opinion? In a NASA ground station, or really any satellite ground station. It could be used as a mobile test tool, maybe. It's compact, light, has spectrum analyzer functions, oscilloscope functions. It can act as a receiver. So it could be very good for troubleshooting without buying a lot more expensive modems for that. It's probably a good tool for education and training of operations teams, maintenance teams, that kind of thing, including end-to-end link simulations. I already did a couple demos for a couple of the NASA engineers and a few engineers at my company. And some other things, we could use it as a low-cost digital IF recorder, or maybe a baseband data recorder. And of course, the forward work would be adding a lot more blocks, like the PM demodulation with a subcarrier. A modulator, of course, is not included yet. I'll need another dongle. Coding and Doppler. Now the equalizer, if I can get the demo going, I've already added that to the flow graph. So let me see if I can get that running really quick. I should have a few minutes, right? That was the end of my charts. Be careful here. It seems
it's already running on the screen.
Oh, okay. All right. Okay. So everyone can see it. So that's the symbol synchronizer right now. After the symbol synchronizer, it's synced up and it's rotating there. The static one on the bottom is the 1010 bit for each tip of the triangle. And the spectrum is there. Since it's a 1010 repeating pattern only, you can see just the spikes at 512 kilohertz there. Can I push this one down? Since yours is on here. Okay, no, okay.
It is your mouse.
Okay, yeah. Oh, okay, good. Okay, I got it. Here's the rotation. You can see that one. On the vendor modem, it was kind of more constant and slower. This is a $90 signal generator. It probably doesn't have a great oscillator, but it still works. The IQ constellation on the bottom is right after the Costas loop, so it's pulled it out, gotten rid of the residual frequency offset. And then the one at the top, the one that says ABI, we call them adaptive baseband equalizers. You can see that the constellation has been tightened up. So this is basically what I was looking for. So I think that was really it. So hopefully that was useful and worth the wait. So that was really it. Okay.
Thank you.